All right. Dr. King, is Dr. Sun can be reached?
Yeah. Dr. Sun Hao is joining in 1 minute. Just now he was starting try to set up the display name, but that's okay.
All
He's
right.
joining. Yeah.
Okay. Thank you. Thank you very much.
Okay.
Okay, we will begin in 1 or 2 minutes. Thank you all for your patience. Keep waiting. All right. So before that, let me share again.
One question first. Dr. Sun said he joined, but asking us whether we can hear him. I didn't see him here yet.
I also can't see him yet for now. Not yet, I think.
Okay.
Mm-hmm.
Not yet seeing you. So, do you use our Gmail ID or your own?
Again?
I think. Only if he uses Silvaco Gmail account, then you are able to see him, right? Otherwise, he will be in one of the audience, maybe.
I see. So it's okay. I think we shall begin first because Dr. Sun will be the second speaker to speak for about 15 minutes for his presentation. I think, shall we begin first while waiting for Dr. Sun? Okay, thank you. Thank you, Dr. King.
Yes.
All right. Assalamualaikum and a very good afternoon. First of all, I would like to say thank you and welcome everyone to another Let's Talk series brought to you by IEEE Electron Devices Society Malaysia chapter. Today's topic will be on semiconductor device modeling. I am Nurul Ezaila Alias, an executive member from IEEE EDS Malaysia. I am also a lecturer from University Technology Malaysia. I will be moderating the session today. Thank you to our panelists today. The first panel is Professor Dr. Anis Nurashikin Nordin. She is a professor from International Islamic University Malaysia. And second speaker is Dr. Sun Tao. He is a TCAD application manager from Silvaco, Singapore. And our third presenter and our third speaker is Mr. Muhammad Amri Ismail, a device modeling engineer from MIMOS, Malaysia. Thank you for spending time to present here, and also thank you to all attendees for this session. I am sure all of you would love to know about our speaker today. Therefore, I will introduce their short biography before they begin their presentation. Just a short reminder. So each speaker will be giving their presentation for about 15 minutes. At the end of the session, we will be having a Q&A session. Please write down your question and drop in the chat box if you have any. So without further ado, let us begin the talk. Our first speaker is Professor Dr. Anis Nurashikin Nordin from IIUM Malaysia. She will be giving her speech entitled Modeling MEMS Devices Using CST and COMSOL. Let me read a short biography of Professor Anis. So Professor Anis Professor Dr. Anis Nurashikin is a microelectronics engineer and a researcher at the Department of Electrical and Computer Engineering, International Islamic University Malaysia, Kuala Lumpur. She obtained her Bachelor Engineering in Computer Engineering from IIUM and both her Master Science and Doctor of Science in Microelectronics and VLSI from the George Washington University in 2003 and 2008 respectively. She has been teaching courses in electronics engineering at IIUM since 2003. She has extensive international collaborative network and served as an invited researcher from Linköping University, Sweden, City College of New York, USA, Griffith University, Australia, and University of Twente, Holland. Her area of specialization is in the field of microelectromechanical system MEMS. With that, please kindly mute your microphone and let us all welcome Professor Dr. Anis Nurashikin Nordin. The platform is yours, Prof. Thank you.
Thank you. Thank you, Dr. Ezaila. Okay, so just give me a few minutes. I will share my screen. Okay, so everybody can see my screen now?
Yes, Prof.
Yes?
Yes,
all right.
Prof.
Okay, Bismillahirrahmanirrahim. Thank you, moderator, for the kind introduction. So my name is Anis, and I'm going to give you a talk on the MEMS modeling. And I've decided today to give you a brief introduction on the two modeling software, COMSOL and CST. Okay, so what is MEMS? The outline for today, what is MEMS, MEMS modeling flow, and then I'm going to give you an example of using CST, using a MEMS resonator sensor, and using COMSOL, MEMS quartz crystal microbalance, and finally I will conclude. Okay, so what is MEMS? MEMS is miniaturized mechanical or electromechanical elements made using microfabrication process. The dimensions, at least one dimension of the structure should be of the size of 1 micron to 1 millimeter. MEMS is usually merged with microelectronics, and it can be fabricated using mature integrated circuit fabrication process. So basically, components of MEMS include microsensors, microactuators, microelectronics, and microstructure. So I think since this is an IEEE platform, I think most of you are familiar with the CMOS process. So the process involves using these layers, metal layers, silicon dioxide layers on top of silicon. Usually, this integrated circuit fabrication process is used to make transistors or switches, and these switches are in the nanometer size. So this is the traditional integrated circuit fabrication process. So in MEMS, we use these processes to make mechanical device and electromechanical devices, which have various applications. So among the applications are sensors, and as you can see here in the image of acceleration sensors in the car, the sensors in the tire for the acceleration sensors, in the airbag, and other contact sensors. There are multiple different sensors which are manufactured using this CMOS process. So this is an image of interdigitated transducers which are microfabricated using the CMOS process. So as you can see, the structures are very tiny, and these tiny structures can be used to detect a lot of either mechanical applications or electrical applications. So why is small important? Because the smaller sensors save a lot of area and therefore save a lot of cost. It requires less materials and samples, and it requires short processing time. You can mass produce a lot of devices because they are small, and therefore they are often cheap. So in biomedical MEMS devices, they are often disposable device. And microscopic structures, they can be used to gain a lot of extra features. You can have strong fields, strong electric fields in a smaller area. You can use these microstructures to detect laminar flow, and these microstructures have high surface to volume ratio, and therefore this results in high signal to noise ratio signals. Okay, these smaller structures also have smaller mass. Okay, so for today's talk, I will talk about sensors, specifically in the biomedical application. These small sensors can be used for health and wellness, for rehabilitation, for early detection of disorders, and for efficient treatment. And it can be also used to monitor the safety of the person. Okay, so my first sensor was done by my master student, Farhan Effendi. And this was done in collaboration with XLIM, University of Limoges in France. So this sensor is actually based on interdigitated transducers, and this sensor is an RF sensor which is used to detect dielectric permittivity. We want to use this sensor for the non-invasive detection of glucose in the body. So if you have a wireless sensor, a wireless detector, it can allow continuous monitoring. It is small and wearable, and it allows real-time measurement of blood glucose. Okay, so just a brief overview on what the sensor is. The sensor, as you can see before, it is actually interdigitated transducers. It has these lines are known as interdigitated transducers, and this will produce electric fields over here, and you can detect the material under test, the permittivity or the dielectric permittivity under test. Using this, we can detect the permittivity of blood glucose. So this sensor, as you can see here, it will vary. The resonance frequency will vary based on the spacing of the transducers. So you need a simulator to determine what is the optimum design to be able to have a sharp resonance frequency. So this is the basic flow of a MEMS design and simulation flow chart. Basically, you do the design and then you run the simulation. And today, this is what I'm going to show you, the Cst simulation for this biosensor. Then you fabricate and you measure and you compare with your simulation results. If your simulation, if your experimental results do not match the simulation, then you have to repeat the process until the end. Okay, so Cst simulation is usually tailored for RF simulations, right? So you can make it by creating a new project under the Cst simulator. It is used for simulation of microwave, RF, and optical devices. Okay, so in Cst simulator, you can draw the 3D model over here, and you can choose the material that you want for the sensor. In our case, we are using materials from the Cst library, such as the printed circuit board, which is the substrate, and copper, which is the electrode. Okay, these are some information about the size and the width of the device. So you can see the parameters over here. You can draw according to scale. For example, what is the length, what is the width, what is the substrate material. Okay, so this is the transducer. And then we will apply a signal at the in here. This is a one-port device, meaning it only has one input and output port. So we will want to see the frequency response over here. So we can select the waveguide port in the Cst simulator and use the solver to calculate the S11 parameters. So in the simulator, you can specify the materials, what is the permittivity of the material surrounding the sensor, and the permittivity of the material underneath the electrode, and the substrate layer. Okay, so based on the Cst simulation, what do you get? You can get the electric field distribution over here. This is the results on the right. And this will show you the electric field surrounding the interdigitated transducer. Okay, you can also plot the S11 over here and to see what are the different results with different interdigitated transducer spacing and width. Okay, so here you can see if you make the width wider, yeah, you have a shift in the resonance frequency. Okay, so now we will simulate the different permittivity because we want to put in the blood glucose over here. So we add another layer over here. It is shown in red, and you add a block, and the block has the blood permittivity values to observe the sensor response in presence to the blood. You can specify the permittivity of blood manually in the material option. So here are the material properties. So you have different permittivity values corresponding to the different glucose concentration. And you can see that we are going to model to see what will happen to the response in the resonance frequency shift. Okay, so here is the results. So you can see with different dielectric permittivities here, you can see that there is a shift in the resonance frequency. And if you have a very high dielectric permittivity, you can see that the resonance is even dampened. Okay, so this is the first sensor. Now the second sensor, this is a dengue detector sensor. This was done by my PhD student. He already graduated. His name is Ahmad Anwar Zainuddin. It was done in collaboration also with Exlim University of Limoges and Linköping University, Sweden. So the sensor is over here. The sensor is actually a quartz crystal microbalance, the one that I'm showing today. And it is a piezoelectric material. Quartz is a piezoelectric material with electrodes at the top and the bottom. So we will want to see how we can model this microbalance and see its resonance frequency. So here you can see in COMSOL, similar to CST, you can draw the model inside COMSOL. Over here, you have a singular quartz crystal here in the middle, and this is on top of the piezoelectric layer, which is quartz. So the gold electrode is only very small. This is the radius of the gold electrode, and this we specify the thickness of the quartz. So the resonance frequency will vary based on the thickness of the quartz. So as you can see here, similar to CST, you can model and find the resonance frequency over here, which is at 9.85 megahertz. In the next simulation, he simulated the quartz crystals in an array. Here there are 4 of them. The quartz thickness is the same and the radius is slightly different. Okay, so you can see over here we can get the resonance frequency, which is close to the actual resonance frequency, which we want of the singular, which is 9.85. Okay, so here what we wanted to do is that we wanted to vary the spacing between the 2 sensors to make sure that they do not interfere. The vibration of the crystal of one sensor does not interfere with the next adjacent sensor. So this is the simulation. Other than finding the resonance frequency, you can also do a 2D and 3D model. And you can see the displacement or the mechanical vibration within the sensor. So you can also perform these plots and you can see the vibration and the displacement of the material. So the area where the highest displacement is where usually where the resonance occurs. So we would want to place our electrode at that point. Okay, so this is another, this is the displacement results at 10 megahertz. And this one is with different thickness. As you can see, when you increase the quartz thickness 500 micron, the resonance frequency will now drop to 3 megahertz. So you can do all these simulations and find out which is the optimum resonance frequency for your specific application. Similarly, you can do the 2D and 3D simulations at this, and you can also increase the array. Here we increase it to 6 and see whether the interference will affect each vibration of each singular sensor will affect the neighboring sensors. So you can see here that each one will produce its own resonance frequency, and they may be slightly different from each other. Okay, and you can also place the displacement. You can actually graph the displacement. This is the displacement. This graph before this one, you can also measure the displacement here, and you can see this is the spacing. You can vary the spacing, where the spacing is 12.5 micrometer, 17.5, 20, and you can see that when they are close together, the resonance will interfere with one another. But when they are spaced apart, they are each resonance frequency is sharper. So here you can see 15 mm or 20 mm is better spaced for the resonance for the crystals. So okay, I'm almost to my 15 minutes, so I will conclude here. MEMS devices basically can be modeled using different software depending on its application. CST is more suitable for higher frequency RF devices. COMSOL is suitable for transducers, electromechanical, electromagnetic, or fluidic devices. So you can select the software based on the physics of your device. So just a short advertisement. I am from the VLSI MEMS and Research Unit, International Islamic University. We are now currently looking for students for all these topics. We have, alhamdulillah, we have obtained several grants. So we are looking for enthusiastic masters and PhD candidates. So if you are interested in joining our team, please email the email below, rosmi@iium.edu.my, and here on the left are all our collaborators. Thanks. This is the picture of our team, current team. Thank you.
Thank you very much, Professor Dr. Anis. Thank you very much for a very impressive presentation. So myself, I personally think that you have brought and introduced the CST and console TCAD to a different paradigm, especially for the MEMS devices and sensor. So this is also a good opportunity for all the candidates. So please email Prof. Anis if you're interested to join her research group. All right. So thank you very much. Like I said, so we will begin with the second presenter. So our second speaker. So we brought to you all the way from Singapore. Okay, Dr. Sun Tao from Silvaco, Singapore. He will be giving his presentation entitled Silvaco TCAD Application on Various Technologies. So before he begins his speech, so let me introduce his short biography. So Dr. Sun Tao has over 15 years industry experience with PhD degree in microelectronics. Before joining Silvaco, he worked for leading semiconductor companies including Global Foundries, Tower Jazz, and HH Grace. Currently, he is a TCAD application manager for Silvaco Singapore. With that, please kindly mute your microphone and let us welcome Dr. Sun Tao. The platform is yours, Doctor.
Okay, thank you everyone.
Thank you, Doctor, for joining us today.
Okay, thank you. Let me share my screen now.
All right. So, Dr. Sun, you can share your slide presentation.
Yeah, just hold on.
All right. So, while waiting for Dr. Sun, if you have any question, you can write down your question and drop in the chat box. So I will read during our Q&A session. Thank you.
So can you guys see my screen?
Yes, I can see very well. Thank you.
Okay, good. Hello, everyone. Good afternoon. This is Sunto speaking. I'm from Silvaco, Singapore. Today, I'm going to share with you Silvaco applications on various technologies. So I will give you a general introduction on TCAD and our Silvaco TCAD flow. So I think it's quite simple. What's a TCAD? TCAD is technology CAD. It includes process simulation and the device simulation. With process simulation, we can use the TCAD to do some front-end simulation such as implantation, oxidation, diffusion, those kind of process step. We can also do medium flank and bicam simulation to realize a bicam structure to extract the bicam RC parasitic resistance. So after process simulation, we can do device simulation. Then we can load this process structure into a device simulation tool. In our simulation tool, we call it vector device. Then we can do some physical-based equation to calculate the electron hole distribution, and we also can calculate the current to extract your IV curve. So this is a different application for Silvaco software. The first group is a display. Our software can support a very good display technology. For example, for TFT, LCD, LED, and OLED. And actually, our tool is quite popular in display market. For power application, actually, it's also a strength from Silvaco. We have a very good power simulation TCAD tool. We support BCD device, the super junction device, wideband semiconductor such as silicon carbide and gallium nitride device. For reliability, we support some normal standard foundry reliability simulation such as for carry and BTI. We also support some single event effect. This for space application. For optical part, we support CCD, CIS, laser, solar cell, photodiodes, those kind of device. For advanced part, we support FinFET, FDSOI, 3D NAND flash, and STRA and the TFET for advanced technology and device. So this is a Silvaco TCAD flow. So first we need a layout tool to check your layout, to do a layout-driven process simulation. For example, in our simulation tool, we have two parts. The first part is our new product we call Vector Family. Another part is our legacy product we call Asina. So after we do a process simulation, we can get structures and we can load the structure to do a device simulation to extract your electron and the hole distribution and your IV curve, and then visualize your result and visualize your insight of your device. We can also using RC extraction tool, we call it Clever, to extract the structure from process simulation to extract your bicam, parasitic resistance and capacitance, and extract a spice-like mist. So first I will introduce our TCAD interactive tool called Tony Prot and the deck build. So this is our GUI tool for deck build. We can use this tool to build your deck to run a simulation. So after simulation, we can do some visualization on your IV curve. This is we call Tony Prot. Can check your IV curve. We can also visualize your inside of your device, such as your potential distribution and implantation kind of parameter distribution. So okay, this is interactive tool. We can use this tool to visualize your device inside. So next I will introduce our process simulation tool. I just mentioned before, we have a tool family. The first one is a Vector Family. It's a new process simulation tool. We also have our legacy product we called Asina. Asina is from our Stanford. It is from Stanford University. So for vector process, our new product, we support very detailed physics-based simulation. We also support rapid prototyping simulation. For very detailed physics-based simulation, we call vector process. It can do very detailed physics-based simulation, such as implantation, those kind of quite complex etching, and IBUs kind of quite complex process simulation, but the simulation time is quite long. So it's just required for a very small device. You need very detailed physics-based simulation. We also have a very robust rapid prototyping device simulation tool. We call it vector processor. It can realize very big structure, especially for some very big complex structures such as 3D NAND flash cell. You see, this structure is quite complex. We also support very complex 3D geography structure such as a FinFET. This is another example we can using this rapid prototyping tool to simulate a very complex structure. Structure is inverter chain to get very early feedback on your device. So this is a process mean to introduction. As I mentioned, we support very detailed physics-based simulation. This is a split gate MOSFET. And this is a process simulation tool, step by step. It's a very advanced technology load. We also support string Gemini epitaxy. This is for FinFET application. For oxidation, for compound semiconductor, we also support a very complex oxidation for string carbide device and also for aluminum gallium nitride device for oxidation. So for gallium nitride device, we also support very accurate multicolor implant, and also we support gallium nitride activation. This is for gallium nitride, and this one is for string carbide. This one is for aluminum gallium nitride. So we support very complex process simulation for compound semiconductor device, not any silicon device. So this is a process step by step. It's a unit process to get a process integration. It's a little process simulation. It's epitaxy process simulation to get spacer, substrate spacer, and this is and the depression. This is SMT process as a patterning. Patterning is little patterning, and we also support the stress and the strain simulation. So next part, when you get the structure, we can load the structure into a device simulation tool. We call it Wicked device to simulate those kind of physics-based equation to get your array curve. So this is some detailed introduction of our Wicked device and also Atlas. Atlas is our latest product. So generally support a 2D and a 2.5D and a 3D device simulation. We also support complex conformal mesh and also the narrow mesh. We support drift and diffusion, the energy balance and the safe heating kind of equation. We also support a customized physics-based model and some customized material parameters for silicon and also for compound materials. We support quite good reliability simulation, as I mentioned before. We support the hot carry and MBTI simulation. We also support radiation effect, this including single unit effect and also include TCAD effect. We also support quantum correction effects, quite important for quantum device, especially in 3D FinFET. And we also support DC and AC and transient simulation, and we also support optical analysis, including FDTD simulation. So next part, we support mixed model simulation. Mixed model means we can combine spice simulation and TCAD simulation in one simulation, which can get very good early feedback on your device performance. It's quite useful for power device simulation. We also support multi-core simulation, means if your CPU has more cores, then it will reduce the simulation time. It's because those kind of simulation, especially for device simulation, is a multi-thread simulation. We also support high processing simulation. It's just quite useful for very wide band semiconductors such as silicon carbide and gallium nitride device, because the band gap is quite wide, so the intrinsic carrier is quite few. So it will create some convergence issue. In this case, you have to enhance your processing to get better convergence on your device simulation. So this is some example to show you our device simulation tool. So this is a quite complex 3D line simulation. It's a stack 3D NAND flash. And this is a SCE file on a 3D FinFET simulation, and this is a FDSOI device. As I mentioned before, we support multi-core simulation. If your core has more numbers, it definitely can reduce your simulation time. So we have a large tool, we call it Wicked mesh. It can link a process to a device. As we know, after device simulation, the mesh may not suitable for device simulation. Normally, we need to some mesh optimization. We have a dedicated tool we call it Wicked mesh. You can load your process simulation structure, then do a mesh optimization, then export to device simulation. It can reduce your simulation time and without sacrifice accuracy too much. So normally for 3D simulation, we support 3D conformal mesh and also support 3D linear mesh. You can say we can do localized optimization based on your junction and based on interface to localize mesh optimization to reduce your mesh load and without sacrifice your accuracy too much. So next round we introduce DTCO. DTCO is a whole flow. Means we can do bytecode and front end core optimization is quite useful for advanced technology load. For example, for 7 nano, 5 nano, you not only the front end device, but also the backend device also need to optimization. We can use our flow to do a core optimization. First, we can do a layout-driven process simulation to get the structure, the node structure to a bytecode extraction tool to extract your parasitic distance for R and C, and also extract the lat list. Then we can also do a process simulation, very detailed process simulation, such as implementation of spacing to get process structure, then do a device simulation, then extract the IV curve for your device. Then we can using our LARA tool we call Atmos to extract your spice model. Then combine your spice model and your lat list and your bytecode RC can do a spice simulation. In the whole loop, we can optimize your process steps such as implementation and also your device architecture. In bytecode, we can also use this flow to optimize your bytecode layout and also can change your bytecode function stack to enhance your secret performance. It's quite useful for advanced technology load such as 7 nano, 14 nano. So next one, I will introduce our LAR tool we call Victory Atom Stick. It's really because when your device becomes smaller, it just have over 10,000 atoms. Then you can using Victory Atom Stick to do atom stick narrow simulation. So this is very useful for very small device such as nanosheet and then nanocarbon, those kind of device. In a very big structure, we can still using our current TCAD to do a task TCAD simulation. In logical block, we can using TCAD to spice, means we can do a paper, TCAD-based paper model to extract spice model to do a spice simulation. So in different structural level, we can do different simulation to meet your requirement. So our Victory Atomic Stick is from NEMO5. NEMO5 is from Purdue University. Silvaco acquired our product 3 years back, and actually this product is quite popular in university and some institute. So this is a press release for this new product. So we can support nano device performance prediction and quantum simulator for very new, very advanced device. So we also have a sales and support. We also have a very good university program for this product. So for Silvaco resource for user, normally we have below resource. The first is menu. You can check menu to check the physical behind of this parameter. We have many examples in that build. We have a simulation standard. We have a regularly. We have a regular webinars and event. And we also have application engineer support. And we also have a very good university program for all the university. So for TCAD manual, actually you can check our manual from our deck build to check to find the manual to check as parameter and check the physics behind those kind of parameter. And deck build, we also have many examples in the deck build. You just load this example to learn those kind of new device, not only for traditional MOSFET and also for atomic level device. So just load those kind of example, learn those kind of example to learn the physics, to learn our software. We also have a simulation standard. In quarterly, we will issue a simulation standard This simulation standard will show you the new feature for our software and also some simulation hint for our software. You just check our internet, you'll find those kind of simulation standard, or the simulation standard has been archived in our server. We also have a webinar to introduce a new physics of your device, to introduce a new feature for our device, for new feature for our software, and then you just need to register it and view those kind of webinar in detail. And all the webinar has been archived in our in the server. So this is an example to show you the latest webinar. As you can see, there's a few silicon carbide device, silicon carbide webinar, and we also have some quite basic training for our new software. So, okay, next I will introduce some application example for 2D and 3D application. This is some one silicon carbide device. Is another silicon carbide device. We can see the column rating. We can do some column rounding design to enhance your breakdown. So in this kind of case, 2D simulation is not enough. You have to using 3D simulation. If your device is 3D bilateral, you have to using 3D simulation. So this is a different column profile. We can using TCAD to do this kind of column design to enhance your breakdown. So this is a different breakdown comparison. We can say with very vertical profile, the breakdown is quite low. We have our early breakdown, but with rounding profile, the breakdown is quite high, almost close to the 1D breakdown. So we can use TCAD as a quite predictor to simulate your device. So in terms of a silicon carbide device, actually we have a very good silicon carbide module. We support a very good oxidation process for silicon carbide, especially for trench MOS. Because as we know, the oxidation rate is orientation dependent, and silicon carbide has many orientation. So different orientation has a different oxidation rate. So when our software can predict those kind of difference. For this example, you can see in the later the oxide thickness is thicker compared to the bottom one. So that means the oxide thickness is orientation dependent. So we also support quite good activation for silicon carbide devices, also quite useful for silicon carbide device, because the dopant is not diffused too much in silicon carbide, but activation is quite difficult for silicon carbide device. So we need very accurate model to predict this kind of effect. We also have very good implant model. That means we have a very good robust non-color implant model for silicon carbide device. This is one example to show you we realize this structure using monocolor implant, silicon carbide oxidation, diffusion, activation to realize structure, then do a cool mode simulation to optimize your device. So you can you can check the oxide thickness is totally different from the bottom side and the lateral side, because the orientation is totally different. So the oxide thickness is totally different. So you need very accurate model to model this kind of effect. So as I mentioned, we can using TCAD to do optimizing on your device. So this is a optimization tool we call WWF to optimize the doping profile to enhance the breakdown. So that means we can do some DOE design to optimize your doping profile to enhance your device performance. Okay, this is some simulation comparison with detailed doping profile optimization. We can enhance your breakdown. If your device design is not good, it will show early breakdown for your device. So actually, TCAD is quite a robust tool to predict this kind of effect. So this is another example to show you in terms of gallium nitride device. We also have very good process simulation, simulation physics. We also support monocolor implant for gallium nitride device. We also support quite good activation for gallium nitride device. So okay, this one comparison between the traditional TCAD and the process-based TCAD. In traditional TCAD, we can using very simple rectangle mesh to realize the structure. But you can see this topography is not consistent with real device. So in this case, you have to using physics-based and process-based simulation tool to get quite accurate topography and do the device simulation. So in traditional way, it's quite rough, but in process way, it's quite detailed physics-based simulation, and the result is more accurate than before. So we also support, in terms of capacity, we also support external stress as well. The 2DG has will be impacted by your external stress. We can put nitride film or depth some metal to get compressor stress and tension stress to enhance your 2DG or reduce 2DG. This is some detailed comparison stress, and this is strain. And this is IV curve comparison with different stress. We can see with compressor stress and tension stress. So, okay, the next one is FinFET simulation. We also support a very advanced technology such as FinFET and Ezaila. As I introduced to you before, we support very detailed physics-based simulation. We can do very good string Gemini epitaxy for substring area. So we also support very good device model such as PQP model and energy balance model, because for smaller devices, kind of effect is quite important. So this is another example to show you a FinFET device. We can do a single event simulation on a FinFET device. Means ion will strike into this device to generate the electron and hole pair, then burn on your device. So this is a detailed from process to device device-based simulation. So this is I will call extraction. This is a voltage comparison. We can say we extract it will show a current spike on your device, and this current spike will generate many heat. This kind of heat may burn out your device. Okay, this is an introduction on advanced device for FinFET. Okay, that's all my introduction. Any question?
Thank you for your presentation, Dr. Sun. All right.
Yes.
So, okay. So actually, we have another one speaker to present his speech. Okay, later on, at the end of the session, we're gonna have a question and answer session. Is that okay with you?
Okay. Thank you.
Okay, thank you very much, Dr. Sun Tao, for a very impressive presentation. So myself, I've been using Silvaco. So I personally think that Silvaco is a powerful TCAD tool, and it is also a great tool for various electronic devices simulation. Thank you, Dr. Sun.
Thank you.
Now I present our very final speaker, Mr. Muhammad Amri from MIMOS Malaysia. He will be giving his presentation entitled SPICE Device Modeling for Research and Manufacturing. So let me read a short of his biography. Mr. Muhammad Amri received his bachelor degree in Communication and Computer Engineering from University Kebangsaan Malaysia in year 2000 and master's degree in Electrical Engineering from University Technology Malaysia in 2009. His past experiences include research and development in semiconductor device model extraction for circuit simulations, characterization of statistical mismatch model, process and device simulations with TCAD tools, qualification of process design kit, as well as development of discrete trench power devices. He is currently working on the research and development of graphene field effect transistor from simulation and modeling to actual device fabrication in supporting nanomaterial technology platform. With that, kindly mute your microphone and let us all welcome Mr. Muhammad Amri. The platform is yours. Mr. Amri, thank you. You may begin your presentation. Thank you.
Okay. Assalamualaikum and a very good evening, everyone. Thanks to the moderator, Dr. Nurul, for giving the introduction about myself. Thank you also to the IEEE EDS team for inviting us here in this online forum to give some talks about semiconductor modeling. Today, I will present some slides entitled Spice Device Modeling for Research and Manufacturing. As compared to the previous two speakers just now, the material that I have here is actually another aspect of semiconductor modeling, which is called spice device modeling, particularly for circuit simulation purposes. This is the outline of my presentation today. I will start with some introduction, a bit about my company, myself, the objective of the presentation. After that, the importance of device modeling, follows with spice modeling in research, then in manufacturing, and finally the summary. Okay, as an introduction, quickly about my company, MIMOS Berhad. MIMOS is a homegrown national R&D center. We are a strategy agency under MOSTI. Looking at the main function of MIMOS, we are supporting several aspects. For example, number one, here is R&D and technology trust area. Number two is services for industries and academia. And number three is technology venture incubation. For myself, I am working within this area, number two here. Under the service for industries and academia, we have several departments as shown in this slide. As we can see here in MIMOS, we are actually covering almost all of the supply chain in semiconductor ecosystem, from IC design to wafer fab, and from failure analysis to reliability tests. Okay, again, quickly about myself. My name is Amri Ismail. By job description, I am a device modeling engineer. My lab name is Advanced Devices Lab, and this is my email, amris@mimos.my. MIMOS is my first and only job so far after my graduation day. I'm doing different jobs, which has keeping me busy and relevant in MIMOS. Started with spice modeling, then a bit of process design kit, PDK, and recently also a bit of TCAD simulation works. My experience will be on both R&D and manufacturing staffs. For R&D, during my early days in MIMOS, we are struggling with CMOS technology back then in years 2000, which with 0.35 and 0.5 CMOS technology. Recently, I am working on graphene field effect transistor, and currently I'm working on gallium nitride HEM device development. In terms of manufacturing experience, I've been involved in CMOS as well as power devices of HVMOS and Schottky diode. The cats here are referring to the areas that I'm directly involved during my daily works. So with respect to the presentation title, today I will only wear a spice model kit. Also, as an introduction, this slide shows three main objectives of the presentation. First and foremost, we want to highlight the function of spice device modeling for accurate circuit simulation in semiconductor industries. The second objective is to review some of the trends in spice model extraction for nanoelectronic device and research works. And number three is to share on the general spice model extraction flow in standard manufacturing practices. Done with the introduction, then we enter the second topic, the importance of device modeling. Before further discussion on the importance of device modeling, I would like to share and refresh our memories on some of the terminologies related to device modeling. SPICE is the short form for simulation program-based integrated circuit emphasis. Then there is circuit simulator, which is typically in SPICE format. Then spice device model parameter extraction. These are terminologies that are very much related to several parties in semiconductor industry chain, namely the IC design and also the process engineers. In the middle, there is a device modeling engineer. The overall picture of relationship between fabrication service and IC design department will be shown in this slide. These are the two big departments in semiconductor ecosystem, namely wafer fab and IC design, and they are talking two different languages. Process engineers are concerned about all of the process steps to build the device, while IC designers are busy with their chip design stuff. Process engineers are offering something that is useful to IC designers, and IC designers really need to have the info into their design flow. So how the information can be transmitted? The answer is through the PDK database or PDK, which is provided by wafer fab team. The key component of PDK database is represented by SPICE device model with additional interconnect models and design rules. Only with the availability of PDK database, the IC designers can complete their design targeting for certain fab fabrication facilities for actual chip fabrication. This slide shows the SPICE model is the critical link between the foundries and IC design team. The benefits of SPICE model for circuit simulation are as follows. First is for quick prototyping of design stage prior to committing for actual fabrication. Second is to make an easy design review between IC designers. Another benefit is SPICE model could be used in making measurements which are not possible to do on the bench. And another important benefit is in studying the effect of process and design variations. Complete with the first two topics, now we are moving into topic number 3, SPICE modeling in research. There are a lot of things that we can discuss about this topic, but considering the time allocation and spirit of knowledge sharing, I will only manage to focus on the area of nanoelectronics. Nanoelectronics is referring to the use of nanotechnology in electronic components. There are several devices of nanoelectronics that we can find in the literature, such as carbon nanotube, CNT, graphene nanoribbon, GNR, graphene FET transistor, GFET, semiconductor nanowire, molecular electronic device, and many, many more. From the list, MIMOS has research experience in GFET, and therefore I will using GFET as a case study in this presentation. We have this GFET development in MIMOS during the 12th Malaysian Plan project ended last year. The development of graphene FET transistor or GFET project in MIMOS is started with the fabrication of actual backgate GFET using our own Fab 1 and Fab 2 facilities. The starting material is actually using commercial 4-inch graphene on silicon wafer from Graphenia of Spain. Besides that, we are also using 4-inch mask liner available at MGIT UTM for the patterning purposes. The complete process flow is shown in this table here. We have 3 mask layers: photoresist filtration mask, graphene channel mask, and source drain contact mask. This slide shows the picture of finished wafer with a sea of graphene transistor. There are about 21,600 transistors can be fabricated on the 4-inch graphene on silicon wafer. The right-hand side picture shows the close view of GFET of a few GFETs. The backgate terminal, the backgate GFET is a 3-terminal device. We have source and drain terminal at the front, while the gate terminal is at the back, and there comes the terminology of backgate GFET. After we have the finished wafer in hand, the next step is to proceed with wafer probing. From the electrical measurement, we are expecting to have an ambipolar characteristic from the IDVG curve plot. Unit ambipolar curve is expected due to the nature of graphene channel characteristic, where single device is represented by both hole and electron conduction. The diagram here represents the model parameter extraction flow known as ambipolar virtuous source model, developed by researchers from MIT. In the flow, MATLAB software is used as a model parameter extraction tool. They are using recent trend of device modeling, which is the combination of Verilog A model with commercial cadence pattern circuit simulator. Dirac voltage, which is the inflection points between hole and electron carrier, is one of the model parameters. During the GFET measurement stage, we have found the issues where we do not manage to get the theoretical ambipolar characteristic. The main reason is because GFET is very sensitive to the surrounding environment, which make it difficult for atmospheric pressure measurement. Sensitivity to water molecules makes the contact resistance higher and lowering the carrier mobility. Measuring at atmospheric pressure environment makes the Dirac voltage to be shifted towards very positive bias. This slide shows the test system available in MIMOS, which contains Agilent B1500A device analyzer and manual prober. With this prober, we can only perform the measurement at atmospheric environment and no high vacuum pressure. This slide shows the simulation result of our fabricated defect. From the derivation, the shear resistance of graphene channel is considered at high side, about 3 kilo ohm per square. But considering that it is a new development of graphene device with a lot of limitation to the test system, then it is still acceptable, supported by the data from literatures and also from Graphenia. IDVD plot at the left-hand side picture here shows that the fabricated defect is turned from N-type to P-type device. The IDVG plot at the right-hand side picture here shows that it is a highly P defect where there is no Dirac voltage can be observed even when the gate voltage is more than 40 volts. In order to overcome the issue of no Dirac voltage observation due to high sensitivity of graphene channel to the water molecule, this slide shows the modified model acceleration flow. Remember the slide for the benefits of model for circuit simulation. One of them is making measurement which is not possible on the bench. We have bought a commercial defect sample from Graphenia, which they reported to show Dirac voltage value with high vacuum pressure environment. Then we do some sort of correlation factor from the IDVD plot. With the correlation factor, we use M bipolar virtual source model to simulate IDVD plot with Dirac voltage values. So this slide shows the list of model parameters extracted from MIMOS fabricated defect wafer. This is in original text format and this is in table form. The special thing about M bipolar virtual source model is it contains only 8 parameters of spice, but actually there are a lot of additional parameters defined in separate file of Verilog A. Defined here, AVS_1_0_05. Device modeling work is about curve fitting between measured and simulated data. We can see from the IDVD plot there is a good fitting between measurement and simulation curves. Then from the IDVG plot, we could observe the Dirac voltage is about 3 volts. We have the spice model parameter, we have the Verilog A file, and it is suitable for the next stage of circuit simulation. We have example here for circuit simulation with defect. The circuit known as a frequency doubler. Frequency doubler function is similar to full wave rectifier circuit in CMOS. The advantages of using defect is it only needs one device to perform the function, while we might need more devices in CMOS technologies. Actually, in later stage, we managed to get the ambipolar characteristics from our fabricated defect. This is done by the functionalization of graphene channel with polyvinyl alcohol or PVA material. Even with the use of the standard atmospheric pressure measurement, we managed to observe the Dirac voltage, which is about 1 volt, as shown over here. And we just do another cycle of device modeling work as shown in this slide. Okay, that's it about on the spice modeling in research with the example of nanoelectronics. Next is spice modeling in manufacturing. In general, semiconductor industries, spice modeling communities are concerned about the standardization, the effort promoted by Compact Modeling Council, CMC, in 1996, where the first selected industry model is BSIM-3 from University of California, Berkeley. Then there are several other industry standard models come in as shown in the list here. Standardization in spice modeling is vital because the focus must extend to the entire semiconductor industry. We need the support from all of them, model developers, EDA tool vendor, semiconductor foundries, and IC design house. The processes used to standardization are as follows: accuracy, qualitative and quantitative testing, availability, version control, verification, and validation. Again, as a middleman between all of the different parties, the device modeling work is sitting in the center of the supply chain. We need to have the input of the related model from the model developer. We need to use the parameter extraction tool and circuit simulator from EDA tool vendor. We need to provide the accurate device model, which is part of the PDK to IC designers. With regards to our database in MIMOS, we have model extraction experience in BSIM 1, BSIM 2, and industry standard BSIM 3 for our all good 0.5 and 0.35 micron CMOS. For parameter extraction tool, we are using Agilent IC Cap and HSPICE built-in optimizer. For circuit simulator, we are using Synopsys HSPICE, Cadence Spectre, and UCB SPICE 3. The PDK that we have delivered from wafer fab to IC design is based on Cadence PDK. This slide shows the standard parameter extraction flow in SPICE modeling. It contains 3 important steps in transistor modeling, namely electrical measurement, model parameter extraction, and model verification. Generally, the trickiest part of device modeling engineer life is to have the close fitting between measured and simulated curve of several IV plots. These are some notes on the circuit simulator related to SPICE format. We can divide it into 2, which is SPICE simulator and SPICE-like simulator. Original SPICE simulator is referring to the open source circuit simulator such as SPICE from Berkeley and LT SPICE from the linear technology. These are the freeware which can be downloaded from internet and can do a lot of meaningful circuit simulation works. On the other hand, there is also the so-called SPICE-like simulator, which is referring to the commercial circuit simulator. Here we have a long list of simulators, but the top ones will be as follows: SPICE from Synopsys, Spectre from Cadence, Smart SPICE from Silvaco, and Eldo from Mentor Graphic. I personally have the experience with circuit simulators such as SPICE, LT SPICE, HSPICE, and Spectre. The beauty of this simulation art is that even if they are different in names, the source code, or even the EDA to supplier, the simulation result should be identical for a similar simulation input setup. Towards the conclusion of my presentation, the table here shows the comparison between device modeling in research and in manufacturing. As we can see, for research work, the advantages are in terms of new physical model development, applicable for latest advanced technology, and huge windows for improvement. Whereas for manufacturing work, the advantages are in terms of scalability, EDA tool support, model verification, and the concept for design for yield. There are still a lot of collaborations that can be done together between research and manufacturing peoples. Close collaboration should further provide quick turnaround time for the new advanced device and technology development. Finally, we come to the summary. From the materials that I presented just now, I would say that SPICE device modeling work is vital because it is a bridge between Fab Foundry and IC design teams. There are a lot of new opportunities in SPICE modeling work with respect to emerging of latest semiconductor technology such as nanoelectronics. Close collaboration between universities, research institute, and fabrication houses are critical for quick prototyping of recent advanced semiconductor devices. With these summaries, I would like to end my presentation here. Thank you very much for your attention. Thank you.
Thank you very much, Mr. Muhammad Amri, for a very impressive presentation. Thank you. So it's an eye-opener. So what is, we know what is a device modeling engineer really do. And also, I think you have brought SPICE modeling for the development of graphene FET to a different standard. Thank you, Mr. Muhammad Amri. Therefore, thank you all for staying with us. Now we begin and we open the floor for question and answer session. So you can turn on your microphone and also you can also drop your question in the chat box. All right. So I can see from the chat box there are some questions to Dr. Soon, and Dr. Soon already gave the answer to the chat box. And there is one question to Mr. Muhammad Amri. Okay, is it possible to model and simulate NEMS devices like nano electromechanical resonators using SPICE?
Yes, generally yes. There are other researchers which are doing that simulation, but for myself, I don't have any experience with NEMS or even MEMS.
I see. Okay, right. So I will
Generally,
just
it can be simulated. Yeah.
okay. So for the Q&A, I will just go with one speaker to another speaker and another speaker. So is that okay with all the speaker? Okay, I have question to Prof. Anis. Prof. Anis.
Yes.
So Prof, I know that from your presentation, I thought that CST and COMSOL embedded, I mean CST is embedded soft tools in COMSOL, but it is actually two different tools, right, Prof?
Yes, it's two
So
different tools.
CST is more on RF devices and COMSOL on the transducer part, isn't it? So in your research, did you use both to develop the overall sensor simulations? And also, did you validate the simulation with experimental work? Thank
Yes.
you.
Okay, so actually we normally start to model MEMS devices using COMSOL multiphysics. However, when we wanted to do the first resonator, which is the RF resonator, the COMSOL doesn't operate at such high frequency. So then my student decided to model using CST. And yes, we model, we also fabricate the device and we confirm the results, and the simulator results is quite close to the experimental results.
I see.
So
Okay.
actually you need to check on there are many tools available, only maybe it might not be work very well for your specific application. So you have to explore maybe all kinds of software.
Thank you, Prof, for the answer. All right, so I can see a lot of questions for Dr. Soon in the chat box. So one question, Dr. Soon, what is the difference between SPICE and Atlas? What are their strengths?
Yeah, actually, Atlas is a TCAD tool. TCAD tool can do physics-based simulation. So it's more like a physics simulation tool, but the SPICE is another story. You need SPICE, extract a SPICE model first. I think for a typical device, you need using TCAD simulation tool, but for very large, such as a very big block, such as logical block, you have to use a SPICE simulation tool.
I see.
They have a different strengths.
Different strengths. It depends on the application, right?
Yes.
Okay, so I go back to Mr. Amri. Okay, so I have question. The zero energy band gap in graphene brings a major hurdle to use in each switching logic application. So due to its low on-off currents, current ratio, is how to overcome the limitation?
Yeah. Actually, based on our experience, the handling with zero band gap properties is very difficult. Even we cannot solve also here in MIMOS at the moment. That's why when we do the actual fabrication, we start to find a lot of hurdles, like and bipolar curve and so on. Then at the moment we solve step by step. For example, by functionalization using PVA. But still, the current becomes, the on-off ratio become lower, and it's not even improved.
That is due to the I-on or I-off?
The ratio is getting lower. I think
because of the leakage current, the I-off.
Probably the leakage current getting higher, probably.
Okay.
So based on our experience, it's very difficult, because if we compare with current CMOS, the value is very high. The issue at the moment with graphene channel is we have a very low current. So that's the issue. I also cannot give the correct answer because lack of experimentation on that part also.
It's okay. At least we have the general idea of it, how to solve the leakage current. Okay, so I go back to Prof. Anis. Prof. Anis, I'm not really familiar with COMSOL, but I know COMSOL is a very powerful multi-physics simulator. So how far the physics explanation in COMSOL? Okay, specifically when we talk about MEMS and sensor.
Okay, so COMSOL, if you want to model the overall device and actually very sort of rigid structures, it is actually good. But if you want to model like the process of MEMS, then COMSOL is not so accurate. So if, for example, our resonator, the device, the fabrication process is not so complex. It only has two layers, only the substrate and the electrode. So the layer is actually very square or rectangle. You can understand what I mean.
Yes,
so
yes.
So you don't need to model the MEMS process. But if you have like reactive ion etching and all this conformal deposition, then COMSOL is not so suitable.
I see. If we have to consider all the process, then COMSOL is not suitable. All right. Thank you very much.
Yeah. If you have a complicated MEMS device, then maybe you need to go maybe like the one, I don't know, Silvaco or maybe Coventoware.
Yeah. All right. Thank you, Prof. Okay. So I have question for Dr. Soon. So there is no more question in the chat box for Dr. Soon, but I have a question for Dr. Soon. So for Silvaco, okay. So I know that if I'm not mistaken, so I know that Tony plot, we can develop the device structure by drawing in the Tony plot. And also Athena offer where we have to do the process simulation, right, Dr. Soon? So how about the accuracy of both devices between two different tools here?
You mean you're talking about Dev Editor, right?
Yes, correct.
Just like a GUI tool to build a structure. This is one way to build a structure. We have another way called process to device simulation, right? It's from Athena to Atlas, or easy from vector process to vector device.
Yes.
So it depends on your requirement. If you want a very early feedback on your device, you better just using
Tony plot. I mean the
Dev Editor or Atlas, because Atlas is physical. It's just a triangle-based mesh. So you can use this way. It can give you very early feedback on your device. But if you want very detailed simulation, you better using process to device simulation tool. It's a whole family. From especially for silicon device, because silicon device is implantation diffusion is quite mature for process model. In those kind of device, you better using process to device simulation tool.
Okay. So when you talk about mesh just now, I think we have students here. I think they also need to know this answer. So how we manage to solve the mesh issue in Silvaco? Do you have any tips on that?
So normally for mesh, we just space avoidance mesh on critical areas such as high E-field area, junction area, and in-phase area. So for our old legacy product, Athena to Atlas, we have one mesh tool we call Dev Editor. Dev Editor is a tool can do localized optimization on your structure. This is for our old legacy. For new product vector family, we have one tool called vector mesh. It can do a localized mesh refinement. We just need spatial avoidance mesh on critical area and loose mesh and non-critical area. It will save a lot of your simulation time.
If we make it dense, then the simulation would take longer time a bit, right?
Yes, we just need a specified mismatch and critical area, such as for MOSFET, we just specify mismatch and channel region. For highway device, just specify mismatch on the high field area. So normally the globe mesh amount will be reduced with this mesh tool. So your simulation time will not increase,
yes,
but reduce. So and also the coverage will also improve with those kind of meshing optimization.
I see. Okay, good tips from Dr. Sun. Thank you, Dr. Sun. So
You're welcome.
I have to go back to Mr. Amri. Okay, so there's let me check in the chat box. Is there any question? Okay, so from myself, Mr. Amri. For the GFAT, electrical characterization, so you compact, since you have the overall process from fabrication and then to the SPICE model. So for the electrical characterization between the experimental work, okay, and also the SPICE model, did you able to get the exact IV curves between those two? And my second question, did your team extend the graphene model, the graphene FAT model to reliability study?
Yes, for the first question on IV curve, yes, we got the IV curves for both IDVG and IDVD. So for the model extraction, we use IDVD to do curve utility measure and simulated data. And then to get the ambipolar curve later on, we actually, after functionalization with PVA, only after that we have the ambipolar characteristic for graphene FAT transistor. So the voltage is about 1 volt, the Dirac voltage. So there is a good step to get the ambipolar from no ambipolar to get it by using PVA functionalization.
I see. All right.
And on graphene FAT, for reliability at the moment, we actually don't do it yet at the moment. Actually we don't have. We have planned previously with our collaborator, university collaborator, but somehow we are not proceed with that, and I'm not sure. Maybe later on, we can perform some sort of simulation using other data and put into the circuit simulation, try to predict the lifetime, for example, of the GFAT device.
I see. Okay. So I have question from my from someone who texts me. So Prof. Anis, is the master application that you showed just now, the advertisement, does that require candidates to do CST and console? He asked.
Oh, okay. Some of it, yes. Actually, we have several projects. We have actually 3 projects running in our research unit. So 2 of them require simulation and 1 doesn't require simulation. But there are about 5 positions.
But all are in sensors application, right? In MEMS.
Yes. Yeah, this is our specialization. So yeah, all of them are in sensors.
I see. Okay, I hope it answers the question. Okay, so I have question for Dr. Sun. Does nanomaterials like carbon nanotube and nanowires are included in Silvaco, and can it be used to build devices using TCAD?
Actually, for those kind of advanced material, I suggest we're using with atomic stick, because atomic stick narrow estimation can simulate those kind of effect. So definitely, atomic stick, this tool can will include those kind of material property.
I see. Okay. All right. I hope that answered your question, Mr. Abdul Rahim. Okay. Okay. So, Prof. Anis, which software you need to simulate RF resonance? So that is CST, right? If I follow your presentation, that is CST. Okay. Okay. So, audience, if you have any more question, you can turn on your mic and ask the speaker. Okay, one more question for Dr. Sun. Does Silvaco can be used to simulate organic devices?
Yes, our Atlas, our class tool, Atlas can support organic device. For example, organic LED. We have this material property base.
I see. Okay. Okay, Mr. Amri. So I have question for Mr. Amri. So for if I follow your presentation just now, the graphene-based FAT you have also extended to the circuit simulation, right?
Yeah.
Your team, okay.
Yeah.
So how far has your team done on the circuit simulation? So is it the CMOS circuit?
No. Actually, the circuit simulation is just to show that the extracted spice model is workable with circuit simulator. There is the link between device model and circuit simulator, because actually to do the actual design with GFAT, there's still a lot of things that need to be developed. For example, all the design rule, for example, that we need to build some sort of PDK, not just the model. Model is one part, and designing the frequency doubler that I use in the simulator is just to show some sort of proof of concept only, to show that the very low A model in graphene transistor is suitable with commercial spectral cadence simulator. So that's the purpose, to show the smooth flow between design, between model and the design.
I see. Thank you. So I maybe missed the presentation just now for the graphene based FAT. What is the length? I mean, for the design?
Actually, the nano part is only the graphene part. The length is 3 micron, and the width about 5 micron.
I see. So the nano part is the nano material lah, based on the graphene.
The graphene channel between source and drain.
All right.
So the nano electronic device. The length is still considered very long. 3 micron the length.
3 micrometer. I see. Okay. Thank you, Mr. Amri. We are approaching to 4:30, so I allow one more question to Dr. Sun. Okay, about using the PDK from TSMC or Samsung. Is it possible to use it in Silvaco TCAD?
Yes, I think Chinda can input more, because Chinda is part of EDA application engineer. Chinda, are you there?
All right.
I was seeing all the audience asking you about the TCAD questions. The Silvaco is not only a TCAD company, we are also in the EDA field. Mr. Muhammad Amri said, we have our smart spice. It's one of the 4 very popular spice, and very early we have that already. Besides smart spice, we also have the modeling tool. We call it Utmost, universal transistor modeling software. Actually, MIMOS have it a few years ago. So talking about the PDK, all the major foundries, we have PDK support with them. And also we have TCAD development for any customer would like to tape out from these foundries. So even if it is not already listed in the foundry's website, we have PDK team that are able to develop that.
Right. So
and the EDA requirement, our company can fulfill as well.
Okay, thank you, Dr. King, for the answer. Thank you. So there are some questions in the chat box. So we have approached 4:30. I think there are a lot of questions. So if you have any question, do not hesitate to email each of the speaker, you may ask them personally. So on behalf of IEEE EDS, I would like to thank all of you for your time to join our session. If we can go further, but time is running out. So thank you to our honorable panelists, Prof. Anis, Dr. Suntao, and Mr. Amri, for your valuable time with us. Great honor to have all of you here. Thank you for your sharing such an impressive research work. So actually we have a full house today. So we apologize. There are some people personally message who cannot come in. Unfortunately, Google Meet only allow maximum 100 participants. We are sorry, but we are very happy to have all of you here. And of course, with the great speakers, thank you very much. So can I request all of you to turn on your camera so that we can have a photo session?
Sorry, my camera is broken.
Oh, but you are the speaker. I see. Okay. So maybe on behalf of Dr. Soon, we might have Dr. King.
I'm enabling my camera.
On your camera.
Yeah, because pandemic, I'm working from home.
Yeah, me too. I mean, not me too. I mean, all of us in Malaysia, most of us work in from home right now.
Okay, reading from the news, it is quite severe recently. Please take good care of yourself and family.
Exactly. Yes.
Thank you.
Yes. Thank you. All right. Okay. So, Dr. Sharifah, ready to take photo?
Okay.
All right. Dr. Sharifah, we might have several pages. Yeah. Okay with you? Thank you, Dr. Sharifah. You might you can call. Okay.
1, 2, 3. Oh. Okay. All right. Dr. Ezaila, do you know how to change the pages?
Oh my God.
I don't know how to go to the other page.
Okay.
But it seems that it's all full here at my page.
Full.
But not really. Some are off the camera. So I think the other page will be off also, because usually if it's on, they prioritize.
Okay, let me just try. I can have maximum pile on my screen. Okay, one more smile, everyone. 1, 2, 3. Thank you. All right. So that's all. Thank you very much. Also, we IEEE EDS Malaysia, on behalf of IEEE EDS Malaysia, I would like to wish all of you happy Independence Day and Selamat Hari Merdeka. Happy holiday tomorrow. With that, please stay safe and vigilant with your loved one. Assalamualaikum and a very nice day. So I would like to share our
Waalaikumsalam.
Okay. Thank you all. Thank you very much. Thank you for your time.
Thank you.
Thank you.
Thank you very much.
Thank you to all the panelists.
Yeah.
Thank you. Thank you, Dr. Soon. Thank you, Prof. Anis. Thank you, Mr. Amri. Thank you very much.
We're all the way from Indonesia.
Yeah. I believe it's from Basuki Connections. Thank you very much.
Thank you. Okay.
Thank you.
Thank you. Thank you. Thank you, Dr. King.
Chairperson.
Thank you so much.
Cinta.
Thank you. Hi all. Thank you.
Bye. Hi, Cinta. Hi. Long time no see.
Yes, later we call.
Yeah, I forward this webinar to Afia also. Yeah.
Okay.
Great.
ASEAN Federal of Engineers. So that's why a lot of ASEAN people coming in.
Okay.
Great. Thank you so much.
Great. We can work together. Yeah, we can work together. I work through with Cinta, no issue.
Okay.
Thanks for the sharing. Very useful. Yeah.
No worries.
Okay.
Thank you. Bye.
Bye.
All right.
Sorry, Doctor. Can we get the recorded version?
Yes, Dr. Shahiman, sure.
Yeah.
We will post the recorded version to the YouTube. I will share with you the link later.
Right. Okay.
Right. Thank you, Dr. Shahiman, for joining us today. Thank you.
Right.